We are Team 17, and we have the Kayak Pak. The agenda for this today is our introduction. We'll be going over our objectives and constraints, then speaking about the testing environment. Then we're going to go into our quality function diagram, also our health and quality, go over some state-of-the-art research, our preliminary design and engineering analysis, then our final design, or the manufacturing process, our final prototype, testing and results, the prototype demonstration, some product changes, final testing, budget, conclusion, and references.
The need statement for our project is that most kayaks have issues with storage and ease of transportation from both apartment adventurers and mass distribution during relief efforts. And our goal is to design a lightweight, collapsible, easy to carry kayak. To meet that goal, we created these objectives. Our kayak should be inexpensive and lightweight. It should collapse into a small carry size so that it's easy to transport. The kayak should be easily assembled and disassembled. We would like it to incorporate a sustainable aspect to go with the adventuring type, and the kayak needs to be able to support a wide variety of users. These constraints measure our objectives. We need the kayak to float, firstly. We don't want it to exceed 40 pounds. The pack size shouldn't exceed 48 by 12 by 12. We would like to be able to assemble it in 5 minutes. It needs to support a rider of 220 pounds. We want the budget to stay under $600, and we want the length and width when fully assembled to be between 11 and 13 feet and 2 to 3 feet respectively. Our testing environment, we did all of our testing here at Tempe Town Lake.
So in the first semester, where all we did was designing the kayak, we developed a quality function deployment that related our customer requirements to our engineering requirements that we saw ourselves dealing with in material options and design options. Our customer requirements are transportability, lightweight, inexpensive, aesthetic, durable, medium weight capacity, meaning wide range of rider weight capacity, easy to assemble, and sustainability. We also compare what we believe our product will achieve to our competitors, which we will discuss our competitors further in a few slides. Our engineering requirements that we saw ourselves dealing with was buoyancy, material choice, bending strength, compressive strength, cost, packing case, double stitch, weight, moment of inertia, and cross-sectional area. And you can see how transportability depended on material and the packing case, lightweight depended on buoyancy, material, cost, and that's how everything related. And then in our house of quality on the next slide, we take our engineering requirements and see how they relate to each other. The material is going to affect the buoyancy. The material and bending strength, compressive strength, and cost are obviously going to have a positive relationship. More quality material and higher quality material is going to have a higher strength and cost more. Our cost and packing case are going to be related directly. Cost and double stitching it. Our upholsterer is going to charge us more for double stitching. And our packing case and weight are going to have a positive relationship. The only negative relationship to note is our buoyancy and weight. As weight goes up, the buoyancy is going to go down. Our state-of-the-art research, as I said, we had two competitors we compared ourselves to. The primary competitor we dealt with is Oru Kayak, which was a collapsible kayak. It takes an origami folding method to collapse down into a collapse state, and this is how we compare to them. In length, we're a little bit longer. In width, we're a little bit narrower. In height, we're a little bit smaller. In collapse state, we have an overall length that's bigger, but an actual volume that's a little smaller and much easier to carry. And in weight, we are much lighter. And also, it's important to note the cheapest Oru kayak you can buy is $1,400, and our kayak drastically comes underneath that. KL Outdoors is our competitor we compared ourselves to in terms of worldwide relief efforts. KL Outdoors actually donated 1,000 of these kayaks, the Aruba 12 SS, in the relief efforts of Hurricane Harvey a year ago. And this is not a collapsible kayak, so obviously the Kayak Pak has a leg up on that front. The amount of volume of transportable capacity you would need for 1,000 kayaks like this is really high, whereas we could probably transport 1,000 kayak packs in its collapsed state in the same amount of volume it would take to transport 30 of these. This is how we compare to them when the kayak pack is assembled. Length, we are longer. Width, we're narrower. Height, we are shorter. And in weight, we are much lighter. Our preliminary design at the end of spring semester shows a 5-foot front section, a 3-foot midsection with an extension joint, and a 4-foot rear section, and then an overall width of 20 inches on the bottom ring, 24 inches on the top side, and a 2-inch offset in the front, back, and on each side, 24 to 20 inches wide at its widest point. Extension joints would be here and here, so we can assemble the frame, drop it into the kayak shell, extend it to lock out with the kayak shell tight on it. On the next slide, the 2-inch offset can be shown in the front, and our hull support locations, and the depth of our hull supports 1/2 inch, 1/2 inch, 1 inch, and 1 inch, and our vertical supports on the sides. So you can see we have 3 on each side, and that was our preliminary design ending spring semester of Capstone.
So here we can see our initial CAD model. This model, which was made to ANSYS, was simulated using a truss support, using hollow aluminum tubing. Essentially, it's pretty similar to the model that was just shown, but being used in this program allows us to conduct a variety of simulations on the model itself. The first of these simulations which we did was a simple structural analysis, essentially simulating the weight of a rider inside the kayak to determine our maximum possible weight on this model. So to do that, we placed fixed supports on either end of the kayak alongside the weight of the rider directly downward in the middle to simulate our worst case scenario of essentially not having a continuous support on the surface of the water. And with our stress concentration points at the bottom of our vertical supports, we came out to have a factor of safety around 7.45, meaning that we'd have to have a rider of well into the hundreds in order to really have any structural difficulty with the model. Additional tests that we did were a simple collision analysis, which we did by fixing the back end of the kayak and then calculating the amount of force that would be applied to it, assuming a 10 foot per second collision. So using this and determining our large points of stress, we ended up with a factor of safety around 11.5 as well.
Once the structural analysis was done, we moved on to a fluent analysis. This was done by subjecting a wetted profile of the kayak, the surfaces that were below water, to a 3-knot water channel. The water flew from front to back, and this was the solver drag coefficient that was calculated with Fluent's solver. Here you can see the water channel vector profile as the water flows from front to back, as I said. Here you can see small vortices forming on the back end of the kayak, and that is what increased our drag coefficient to 0.74.
So in order to calculate the buoyancy factor of safety, we calculated the area in different sections of our kayak. Once we did that, we were able to find the volume. The one assumption we did make was that the water would come up about halfway up the side of the kayak. And so with that assumption, we came up with a factor of safety of 1.73 for the buoyancy, which is we consider safe for our craft. And then just to summarize our calculations, we have the same factor of safety for the buoyancy of 1.73. We have a factor of safety on the structural frame of 7.45, which is sufficient, and then a very low coefficient of drag.
So for our final design this semester, we had made a few changes. One of the most notable changes is each individual section now has 2 vertical supports, and they're welded in place and permanent. We did that so we would have less individual components, easier to assemble. And then also, each section is now 4 feet instead of the variable lengths we had before, and we've also removed the expansion joint.
So we did this is the initial start of our manufacturing process. We actually started out with this wooden jig in order to hold the piece of aluminum that we bent for the upper and lower rails, as you can see in the picture over here. It doesn't have the uprights or the end caps on it, but it's just the rails, and then we secured them to the frame so that we can get accurate measurements for the rest of the manufacturing process. Something interesting with our team, we were able to work with a business, Extreme Fabrication. We actually were able to coordinate some social media platform for them to kind of show what they do at their manufacturing shop. And in trade, we would get some fabrication for free. And so the cost for our fabrication didn't cost us anything. They actually allowed some of our teammates to go out to their shop and do the manufacturing process ourselves and cut these uprights. Some of the more difficult parts that we did were the end caps and bending those to make those the right size. Next slide. And then Extreme Fabrication actually welded everything up for us, which was actually a huge cost that they did for free, and we definitely do appreciate them. And then here on the other side, you can see once we had everything welded up, we started to take off each side of the kayak.
So here we can see some of the changes that we ultimately ended up making during fabrication. The most noticeable one, as you can see in our design on the right, we originally intended to have an upright support running between both of our end caps on each end, and we eventually decided to do away with that because it made it very difficult to actually get the end cap pieces onto the kayak itself. Additionally, it helped simplify our model further. Then the other major change that we made was, you can see on the right that we had not all of our horizontal supports aligned with each other, so we decided to go ahead and put those directly over each other for both simplicity and aesthetic purposes.
For our initial prototype testing, we did not have approval to go to our upholsterer and get the shell made yet. So we took the billboard material that we had purchased earlier in the semester and wrapped it around the frame and placed it in water to test waterproof, leakability, and just make sure overall the frame and the shell were going to work together. I then took this material to our upholsterer to try and get a quote to turn into ASU. And when I first took it to him, he suggested that the material might not be strong enough, so we actually stitched up a little piece. He thought the stitching was going to lower the strength integrity of the material, and he was absolutely correct. And he also had some concerns about him stitching the material up and those seams not being waterproof. So we decided to go with a material called Herculite, which does come in a sustainable form. However, due to timeline issues, we used the Herculite material he had on site. And that material is shown at his shop. First they assembled it all the way around, and this was going to be a zipper, and then during his fabrication, he actually called myself and a teammate in for some design decisions, such as our open bay area, whether or not we wanted the zippers to be symmetrical on both sides, and we went in there and discussed everything with him and got a final design, which we can see on the next slide. Here's our kayak frame, here's our final shell assembled, and then the way that we would put the shell onto our kayak is we slid the back through this opening past the end of our shell to the point where the nose could slide in there, and then slide it back, pull the shell up around the stern of the kayak, and then this flap flaps over and a zipper zips around, and then we have straps here and here that strap together. That way, when you have the buoyancy force acting on the bottom, it doesn't pull the sides down, and the seat sits between those two straps. The final prototype with the seat installed is shown here. The sun's a little bit in the way, but we have a kayak seat that's actually on like this little swing method to where it's actually suspended from the top rails and sitting about an inch above the bottom of the kayak. And that is our final prototype, which we conducted all of our testing in.
So we went out to Teputown Lake to do our testing. We initially put the kayak in the lake at first with no weight in it, and we waited about 20 minutes to make sure that everything was okay and we didn't have any leaks. As we progressed in the testing, we actually brought some weights with us and we slowly added weight to the kayak. We started at 45 pounds and then we waited for about 20 minutes to make sure we didn't have any leaks or problems. And then we slowly increased that weight 45 pounds at a time. continually waiting and make sure we were okay with our kayak. And we did that until we got all the way up to a real rider's weight where we had a teammate actually test out our kayak.
Then later on that day, we met with Professor Kosaraju at Tinkertown Lake to conduct our prototype demonstration. First, we had all the components laid out in its collapsed state, and then we assembled it in front of Professor Kosaraju. Then, after that, we had set the kayak in the water, and I had paddled out into Tinkertown Lake, and around and came back. And up until, so the kayak did float. Overall weight is 15 pounds. It collapses into 50 inches by 14 inches by 10 inches. The assembly time is 7 minutes. The rider weight we tested up to was 145 pounds. The cost came out to be $717.72. Our overall length is 13 feet. Overall width is 2 feet.
After the demonstration, these are the changes we decided to make with our final prototype. We went ahead and color coded the joints, and this would help us with quicker assembly time and locating what pieces go with what pieces. And we also created a user manual with general product information and assembly instructions. We also wanted to lower the seat position to make it more stable and add a silicone seal to the bottom to reduce water or increase waterproofing. With the manual, we went to a group of people and had them assemble the kayak in pairs. The resulting assembly times were 8 minutes and 37 seconds and 11 minutes and 2 seconds for an average assembly time of people unknowing of our project of 9 minutes and 49 seconds.
So here we can see our final budget for the project. So the primary things to note are, as we mentioned earlier, we are a little over $100 over budget. And the primary reason for this was unexpected costs relating to fabrication, which ended up being the bulk of our costs. As we did mention earlier as well, this is even mitigating the fact that we did get our welding and some of our fabrication for free as the result of our social media deal. However, there are some important things that should be noted regarding potential mass production for this product, namely the fact that many of these costs can be reduced significantly or entirely eliminated across multiple build attempts, such as taxes and then our wooden jigs, simply because we wouldn't either be dealing with them in the case of taxes or we'd be able to reuse them as with the wooden jig. And with our welding materials and fabrication costs, we would also expect these to be reduced significantly simply because we wouldn't have to have custom jobs done every single time we were making this product. So in conclusion, we only had two major constraints that we didn't end up meeting, one being our budget, which we touched upon in the last slide, as we would expect that to be more suitable in future build attempts, and our assembly time, and we believe that we were simply overambitious with trying to have an assembly time as low as we were originally shooting for.
In addition to those, we could also do some future testing at full load of 220 pounds and do that for an extended period of time to ensure that the shell is completely waterproof. And these are the references that we have been using throughout both semesters.